afternoon, everybody. There we go. How's it going? How's Ignite going? How many first-timers? Ignite first-timers? Okay, quite a few of you. Welcome to Ignite. My name is Mark Russinovich. I'm Chief Technology Officer of Microsoft Azure. How many people have heard of Azure, by the way? Actually, when I first started doing this talk, that was a real question. So we've come a long way, and what I'm going to show you is some of the latest innovations that we have in Azure, give you a little look at maybe some of the things that are coming, and along the way, frame that in overview, very high-level overview of the Azure architecture. So this will take you inside into various aspects of the Azure platform. Here's an agenda for what I've got. It's a ton of material, and I think that one of the most difficult things for me about this talk is that I start out with a whole collection of demos and cool features, internal information that would end up being like three of these in order. And so I've got to then trim them all down to just a few, and you can see it's just painful cutting it down, and I still am going to cover a lot. So I'm going to be moving very quickly through this. I've got 10 demos for you, and there's some pretty cool shock and awe kind of demos in here. But first I'm going to give you a little background on our data centers, talk about our data center architecture, our philosophy about how we place data centers, where we're going with data centers, some future-looking aspects of data centers, get into physical networking, which is how we connect the data centers together, and what we do within the data center with networking, talk about logical networking, which is the virtual networking capabilities, go into the server design. So I'm going to take you on a history of Azure servers going all the way back to 2010, which is when I joined Azure, show you what servers look like then and the kind of servers that we're deploying now. Go into our compute platform, which includes how we deploy virtual machines as well as containers, because containers are becoming a very critical aspect of our platform, and I'll show you some really cool innovations we've got, including some that we announced this week here at Ignite. Talk about Azure Storage, one of the fundamental building blocks of any cloud application, and we've done a number of things this year to improve the scalability of our storage platform, as well as improve the performance of our disk platform. So I'll cover that in that. And then finally, a brief look at our data platform. So I'm going to show you some things that are going to be coming in Azure Database that should excite any of you that have large databases in Azure Database. And then talk a little bit about Cosmos DB and how that's architected. So let's go ahead and get started by taking a look inside of our data centers. And like I said, I'm going to start with how we place data centers. We divide the world into geos or geographies, and these used to be large areas of the world like Western Europe, North America, but more and more it's becoming a country, and you'll see our geos now mapping to countries. What we believe, our philosophy here about where we decide to create one of these geos and how we define the borders of it is that customers are generally comfortable having their data anywhere within that border of that geo. So within a geo, where we place data centers, we call those regions. And a region is defined by a latency envelope of roughly 2 milliseconds. So we place the data centers close enough together that data can move with ability to synchronously replicate data within a region. And then we also go into a region pair architecture with almost all of our regions. There's only one exception right now, and that's South America, the Brazilian data center region, which is not paired with South Central US. But everywhere else in the world, we've gone in with 2 regions, and the reason we do that is that we want to create the ability for customers to DR from one region to the other. So we separate them by hundreds of miles so that they can tolerate large catastrophic events like the power grid failure, like a hurricane, which is top of mind for a lot of people these days. And we also, to ensure high availability of those region pairs, we update software to them independently. So we'll do one and then the other in case there's a problem with the software update bringing down part of a region. We don't bring down both of the region pairs and customers can fail away. One of the asks that we've gotten for a long time is resiliency to more localized kinds of faults within a region, like a data center flood or a fire or a power outage in a data center. And we've had some of those in our past, and so to have customers be able to protect against those, we've started to roll out something called availability zones. Availability zones are taking a region and splitting into 3 separate isolated data center areas, where those data center areas have non-correlated fault modes. By that I mean is that they're on independent electricity, they're on independent power, they're on independent water, and they're independent physical facilities. So if there's a flood in a data center, it's only going to impact one of those AZs, not the other two. The reason we go in with 3 is that we want customers and us to be able to create storage, persistent storage services that replicate data. And to replicate data with high durability, you need a quorum or a vote on what is the most durable data. And so that means you need at least 3 to achieve that, where you can lose one and still be able to write data with a vote of 2 of 3, with the third one not participating. Customers will see 3 zones, though regions could have potentially more than that. And so we're doing a logical to physical mapping. So here's a hypothetical region that has 4 zones, and 2 customers with different subscriptions might have different mappings of their zones that they see, zone 1, 2, and 3, to the physical zones underneath. Now that's kind of the logical view of how we place data centers. Here's the physical view of how we place data centers. I've got a few pictures here of some of our regions, of some of the data centers in our regions. Here's 2 data centers. They're actually 2 data centers that consist of 4 independent colos, 8 megawatt colos here, so a total of 64 megawatts of capacity is what you're looking at. This is in Quincy, Washington, near the Columbia River, and that reflects our goal to power our data centers off renewable energy sources like the Columbia River. Here's another look at Cheyenne, Washington. So you can see the similar data center architecture there. This architecture is called DC 2015, so it's a few years old. We've got a couple of generations of data center we've created since this one. But this is one of our larger regions, our kind of regions that we are creating to basically be able to expand indefinitely in terms of the footprint that we can put there. Lots of land, lots of power. Here's a look inside that data center. So here's a hallway. It kind of looks like the Death Star hallway, but that's kind of the way it looks. It's relatively boring, and actually what's kind of weird is walking inside one of those things and having contributed to the software that's running on these things, I have no idea what's running on those particular servers. It's just like humming away doing who knows what. Now here's a look at Dublin, Ireland. This is another one of our larger regions. You can see there that there's 2 data centers in this picture, and they're slightly different data center architectures. So we've been building out in Dublin for the last 8 or so years. So data center architectures have changed several times since then. Here's another look at Dublin. So in this picture, you can see another data center facility. In addition to the 2 we were just looking at, this is from a different angle there, that long one across the top, yet another data center architecture. We are always iterating on data center design, and the reason that we do so is to optimize the efficiency of our servers, or try to get PUE down, which is the wasted electricity. You want to maximize that electricity so that the servers are cheaper to run. And one of the ways that we're looking at with Microsoft research on running data centers extremely cheaply is by putting them on the ocean floor. This is a project called Natick. How many people have heard of Natick? So quite a few of you. A couple years ago, there was version 1 of Natick, which made a story in the New York Times. Microsoft research took a very small cylinder, put 1 rack in it, and dropped it in about 30 feet of water for a month, and then pulled it up and said, server's still working, cool. So we didn't learn a tremendous amount from that. But what we hope to learn are some aspects of how we can optimize the energy efficiency of the data center and maximize the lifetime of the servers. And I'll get to that in a second after I show you just what we did in this experiment. What you were just seeing there is the tube that was about 12 meters long, 3 meters wide, had 12 racks in it of servers, and that is then going to be dropped to the ocean floor. And you can see this gantry now, which is going to be floated out 1 kilometer offshore, and then drop the cylinder to the ocean floor in about 100 feet of water. And this is off the coast of Scotland, northern Scotland. Now, once it's dropped on the floor, we need to connect it to electricity and networking. And so you can see this is the tube that comes from land that we connect up to the cylinder. These cylinders can go from being manufactured saying we want one to actually being dropped on the ocean floor in 30 days. And so that's exactly what we did in this case. The cylinder was made in France, and then we had it shipped to Scotland and dropped it in the ocean floor 30 days later. The reasons why we think this can potentially be interesting is that this is a lights out operation. Besides, well, the obvious thing that it's cooled by the ocean water, and it's liquid cooled, so those servers were encased. We have liquid water from the ocean coming in, cooling the servers, is that we're not touching the servers. It's a light-out operation. And the theory is, if we don't touch the servers, if humans aren't manipulating them, if the temperature remains constant, if the water vapor is extracted from the air, and the air is extracted from the cylinder, so it's basically a vacuum, and it's isolated from the outside world, that those servers will last longer. So this experiment's going to last about 3 years. They're sitting there on the ocean floor, and we expect to have pretty good view of server reliability after about a year of operating this. Now, we're concerned about potential impact to the environment, and we've done analysis and shows that we could put lots of these on the ocean floor, and we're just not going to affect even the local surroundings with the heat that's dissipated from these. There's just so much ability for the ocean to absorb so much heat. But nevertheless, we do want to understand if there's going to be any impact that we're not aware of. And so what we've done is mounted cameras down there. And this is actually a feed from one of the cameras. So this is pumping images up into Azure Machine Learning pipeline, which is using a fish classifier that our marine biologists now are looking at. And we're trying to track, how the health of the ecosystem around these tanks. There's actually a live feed on the website for Natick, but if you go there, the camera's covered by seaweed. So we do have to have some people go down there occasionally, not to service the servers, but to clean the seaweed off the cameras. Now let's take a look at physical networking. When it comes to physical networking, our architecture is designed to connect our regions together over our WAN. You can see the fact that we can connect to consumers, we connect to enterprises through Express Route, Direct Connect, and Internet exchanges. And then we've got a regional network, which I'll talk about, which connects the regions, the data centers in the region together, and then to the WAN. This networking infrastructure supports all of our networking services, and you can see a bunch of networking services that are both logical and physical there across the bottom, and that set of services continues to expand. In fact, we've got a couple that I'm going to talk about that we announced here just at Ignite. That dark fiber backbone is one of the largest in the world. In fact, we think it's one of the 2 largest dark fiber network backbones connecting data centers together in the entire planet. And you can see a map of it here, literally tens of thousands of miles of cable connecting our data centers together, including some very expensive projects that we've gone on with other companies to lay cables across the Pacific and across the Atlantic just very recently. About a year ago, we announced the Maria subsea cable connecting Bilbao, Spain. I think we're somewhere in Spain, coast of Spain and Virginia. Now, most of the subsea cables in the Atlantic connect UK and New York, and so this provides an extra level of redundancy for our cables that are there. Plus, it's 160 terabits of capacity, making it the largest bandwidth subsea cable crossing the Atlantic. We also have lots of points of presence. We've got 3,500 peering points with partners, 103 points of presence out there. And those points of presence, I'll come back and talk to you later some of the things we're doing with that. One of the ways that we can make a region scalable is by not directly connecting the data centers together. If you imagine some of our regions as they continue to expand will have potentially dozens of data centers. And if you think of having those data centers all be able to talk to each other, well, you could crossbar them together, but that's going to be a tremendous amount of complexity and a tremendous amount of cable to connect them all together. So what we do is we create what these are regional network gateways, which are redundant. You can see there's 2 physical facilities where the data centers are connected to both of them, and all of them. And so now traffic within a region can stay within that region by going through the regional network gateways between any of those 2 data centers. And then those regional network gateways are connected to the backbone. While that simplifies the topology that we would otherwise have if we directly connected data centers together, managing the routes, managing the ACLs across all of the physical devices we've got across all the 150 plus data centers that we've got operational right now is extremely complicated. And the way that we used to do it was the way that traditional IT does it, is that we've had spreadsheets and files that show the configuration for the routers and the ACLs and the routes, and then we go and would program the routers when we updated or expanded our capacity or changed our routes. What happens in that case, though, and how many of you are network engineers in here? So a few of you. Have you ever misrouted something and black holed traffic? So this is one of the big risks as the system becomes so complicated as nobody understands anymore the effect of a single configuration change. And the wrong one could literally impact all of Azure regions around the world by sinkholing traffic. So a few years ago, we started a project with Microsoft Research to create an emulation of our entire network, a high fidelity one that runs in Azure virtual machines, where the actual physical devices are represented with emulators that we can give the exact configuration we'd give to the real devices to and have them operate the same way they would with bug-for-bug compatibility. In this way, we can, anytime we make a change to our WAN, our routes, our ACLs, we can deploy it to this, run the simulation, and make sure that everything is still connected the way we want to. And we've caught numerous bugs before they've gone out into production. And this is really the only way we could be operating at the scale we're at with keeping network highly available in the face of configuration changes. You can see we've spent over 12 million core hours simulating changes to our network in the last year. So that's a look at physical network, and let's talk about logical. And if you take a look at how we architected Azure from a logical perspective, it's useful to contrast that to the traditional enterprise network architecture, which is based off of appliances that have management, the control plane, and the data plane all within the same box. And when Azure started, that's the way we did things. We quickly, within a year or two after Azure launched, found this to be highly complicated, fragile, expensive, and lacked high availability. Those boxes have no scale-out architecture, and so you just have to buy bigger and bigger boxes. So what we did was start working on software-defined networking before it became a really hip term. And software-defined networking, you take those layers and blow them out into software programs that run on standard servers. So we took management, that's the Azure Resource Management. That's how you program what you want for your virtual network, your virtual machines, your IP addresses, your network security groups. Then we implemented controllers that take the high-level management APIs, translate them into what the goal state, the kind of state that is desired for the collection of virtual machines. And then the controllers take that information and then plumb it down into all the distributed devices, in this case servers, that implement the routes and the ACLs for those virtual machines. So this is virtualized networking at massive scale. So an example of the operations, creating a tenant or creating a virtual network. That virtual network then has ACLs plumbed into it. The control plane takes those ACLs, gives it to the servers on which those virtual machines are running. And the key to this flexibility is that's host-level software-defined networking. Host-level software-defined networking will make sense in the context of the overall Azure architecture, which you can see in this diagram. You can see at the very top, the portal, the command line interface, third-party tools. By the way, PowerShell is not in there. It should be, but I just wanted to annoy Jeffrey Snover, so I took it out. Azure Resource Manager. And then you can see container orchestrators that run on top of virtual machines, along with compute network and storage services. The Azure Fabric Controller, which manages the deployment of virtual machines onto our servers. And on top of that is a hardware manager running on top of the hardware infrastructure, responsible for managing the health and the provisioning of those servers. If we just blow out the network parts of this, you can see that there's a network resource provider that plugs into Azure Resource Manager. It's responsible for implementing the network APIs. And then it's got side by side with the compute resource provider that implements the virtual machine APIs. I'll talk about how they coordinate in a little bit. But the network resource provider then has components underneath it that manage those controllers that I talked about in the SDN slide. Like the regional network manager then talks to the network state manager, the directory service, which keeps track of the virtual network physical to customer address mappings, and then a software load balancer, which does the load balancing. If you take a look at inside of one of our servers, it roughly looks like this. You've got what we call containers, which are virtual machines. Those virtual machines can have containers within them that are now considered first-class objects. There's a node agent sitting on the host, which is managing the creation of those virtual machines. And then there's a number of other agents, including network agents, like network manager agent and the load balancer agent. And those program something called the virtual filtering platform. that is responsible for encapsulating, de-encapsulating traffic, applying ACLs, and applying routes and firewall rules. And you can see that when we, what we do when we deploy a virtual machine, commands come down both to deploy the virtual machine, and then the network stack finds out where the virtual machine is and talks to its agent to wire that virtual machine up to the network. So a number of other logical services that we're building out as part of the overall logical network capabilities include something called the Azure Front Door service, which we announced here at Ignite. I talked about those 130 points of presence, and we're launching here at Ignite Azure Front Door service in about 70 of those. And with this, you can terminate SSL traffic at our front doors. You can do global HTTP load balancing through our front doors. It's integrated with App Service and Azure Web Apps, so if you're using those, it's using that for application acceleration of our front doors as well. And we've been using Azure Front Door inside Microsoft across our properties like Dynamics 365 and Office 365 and Bing and Xbox Live for the last 5 years. So this is us bringing that internal service and making it available for customers to use. Another service that we announced this week is something called Azure Virtual WAN. Azure Virtual WAN is going after the problem where you've got lots of different users running around, some of them that are located near your corporate data center, some of them that are branch offices, some of them are out on using mobile devices, and you want control over their traffic. You want to be able to filter their traffic, you want to be able to do security inspection on their traffic, but getting a handle on it is hard. You could make them all VPN, send all the traffic back into your corporate network, but then you're overloading your corporate network, your devices there, your firewall devices get overloaded. So what we're doing with Virtual WAN is making it so you can very easily plug your branch offices and your VPN gateways into Azure, into a backbone, the Virtual WAN backbone through hubs, so that all the traffic goes up and gets routed to the right places in the cloud. And related to that is the general availability we announced here at Ignite of the firewall service, another logical networking service. In this case, what's behind the scenes is you create a virtual firewall. It's launching virtual machines. It's kind of serverless because you don't see them. We're launching them. We're scaling them out based on your traffic load, the level of service that you've requested. And this firewall can implement level 2 all the way up to level 7 policies. So you can use FQDN kind of rules to block traffic or route traffic. You can use IP ACLs as well on the firewall. You can have the firewall the IP addresses of the firewall be allocated from a specific subnet, making it very easy to set up firewall rules that will scale with your cloud deployments on your own local corporate firewalls. So I mentioned that virtual machines are first-class citizens, obviously, in Azure networking. But up to this point, containers have not been. We're working on a project here called Swift, which we're rolling out right now for our own services and will make available to third parties, that lets an orchestrator program the Azure Virtual Network directly. The idea is you've got a bunch of containers. They belong to different applications that should be in different virtual networks that you're deploying to a cluster. So how do you do that? Because up to now, virtual machines are in a single virtual network. Well, with Swift, what you can do is delegate management of a subnet to an orchestrator. And the orchestrator and a set of virtual machines the orchestrator is managing. At that point, the orchestrator can call into the Azure network agent on the server and assign IP addresses to particular VMs from that subnet range. And then within the VM, it will run a container network plugin that takes that IP address and exposes it to the container, or maps it to whatever the container sees. So in this way, as a container moves from virtual machine to virtual machine, the orchestrator knows which virtual machine it's on and can tell, using an agent, here's the picture, can tell the agent on the host which subnet, which IP addresses from the subnet it's managing. This delegated network controller here is on the master nodes, and will tell the agents that are deploying containers which IP addresses that they should plumb into the host to say, hey, this container's here, the IP address should be this. And might be kind of hard to follow, so let's go ahead and take a look at a demo of that in action. So what I'm going to do here on the demo machine is I've got a Kubernetes cluster, and I'm going to show you that that cluster consists of two nodes, a worker and a master. So here's the worker, and what I'm going to do for this worker now is deploy some pods to it, but let's first show that there's no pods running on this. Get pods. No pods running, so I'm going to run a little script. What this script is doing is delegating a subnet to the Kubernetes master and saying, you can now use this subnet, the IP addresses from this subnet, to assign them to containers on that worker node, that worker VM. In fact, we're assigning two of them, two virtual networks, to Kubernetes. So now with two virtual networks, we can start to deploy containers into one virtual network or the other one. And they're isolated from one another just in the same way two virtual machines would be isolated from one another, even though these containers happen to be running on the same virtual machine. And to demonstrate that in action, let's see if this thing has come up with IP addresses. And it does. They both have the same IP address, even though they're both running, and these are real Azure IP addresses that are assigned to virtual networks, so they're accessible from other virtual machines talking to those IP addresses. And so what I'm going to do is launch a web server on one of them. So I'm going to actually cube control exec-it into this first container. Whoops. Copy, paste, bash, and to show you that this is not a canned demo, what message do you want me to write? Hello, Azure. Let me be correct here. Hello, comma, Azure. Oh, hello, comma, capital Azure. Okay, now let's start up a web server. 23.0.15, I think that's it. Let's put it on port 80. And now, so that web server is running inside one of these containers that's mapped to one of those. Now, I'm going to take from another virtual machine that's outside of these, in a different node from the Kubernetes worker. I'm going to, and that's part of the same virtual network that web server's in. See if I can get that file, and there it goes. Now this other virtual machine is in that second subnet, the one that doesn't have, the one with the container that doesn't have the web server running it. And you can see that I can ping that container, the second container, and to prove that it's actually a different container, even though it's got the same IP address in a different virtual network, and there. It's not running the web server. So what we've just done is showed two containers. They've got the same IP address exposed to, from virtual networks, two different virtual networks in the same virtual machine. And so this allows now containers to have the same network policies applied to them as virtual machines do, first-class citizens in the Azure network. So let's take a look inside of our Azure servers now. And again, I said I was going to take you a walk down memory lane. Starting with our Gen 2 machine, you can see I've got ratios of core and RAM there at the top to give you an idea of how we've grown over time. Because in the original days, we started by kind of scale out commodity servers. So this server has 32 gig of RAM in it. It's got a 1 gigabit NIC in it. It's got no SSD in it. So it was an awesome machine back in 2010. And then we introduced our Gen 3 machines, got slightly larger. We introduced 10 gigabit networking, then 40 gigabit networking, started to introduce SSDs. Then we introduced a scale-up machine. We called this one Godzilla, because at the time, it was one of the largest servers in the public cloud. It had 512 gigabytes of RAM in it, so you could have a virtual machine with roughly 450 gig of RAM in it. And this was to run scale-up SAP HANA workloads, other in-memory databases. We had lots of enterprises starting to migrate HANA. Then we introduced our Gen 5 general purpose machine, and you can see it's half the memory now, or more than half the memory of our Godzilla. So starting to get bigger general purpose machines. Then here's our Gen 6, which we are in the process of deploying now. But then we had customers coming to us and saying, we've got even bigger SAP HANA workloads. They don't fit in your Godzilla. What are you going to do for us? So we introduced this. And this is called the Beast. It's got 4 terabytes of RAM in it. But you're impressed at that? Well, they came and said, OK, that's good, but we've got even bigger SAP workloads. So we've just announced this, Beast V2. It's got 12 terabytes of RAM in it. Now, you might ask why it's called Beast V2. Why didn't we call it Son of Beast? Son of a Beast, I guess, it would be better. Or Beauty and the Beast. Turns out there's a movie, some kind of movie that has that name. But anyway, so we just came up with Beast V2. But let me show you Beast V2. Oh, by the way, we also have Sphere. That's another one. OK, so here's Beast. So I'm going to show you one of my favorite tools. And show you just how much RAM this thing has in it, just for real. All right, whoever wrote this, it's like cut off. It's got a negative number here. This is a sad, sad day. I've got to run this tool instead. So how much RAM does this have in it? There it is right there. So Notepad is amazingly fast on this thing. And you can actually open 7 Chrome tabs in it without any problem. OK, so now we've also got special purpose servers. So here's HPC SKU. We started to introduce GPUs. So one of our first GPU series had a K80 processor for general purpose compute on GPUs. We introduced high performance computing VMs. They have InfiniBand networking. In fact, they've got 100 gigabit InfiniBand networking connecting them together. We introduced high performance computing SKUs that are compute intensive, so they run at higher frequency and have more cores. And then we started to introduce deep learning SKUs. So the NDV2, this one has 8 NVIDIA V100s cross-linked together with NVLink in a 4U server box. So those things consume quite a bit of electricity. And then here's the LV2, which we're also announcing. This is a high-density SSD SKU for database-type applications like a Cassandra or a MongoDB that store data locally on the SSDs and want high performance. We provide high performance with this SKU using something that's part of server called NVMe Direct. So we expose the SSDs directly, the SSD I/O queues, directly into the virtual machines, map them directly into the virtual machines so they can directly access the I/O queues, putting commands into it and reading the results out of them. But we put filters on the command queue so that the VM cannot do something like flash the firmware or other things that it shouldn't be doing to the SSD. So this provides security while giving the VM native SSD performance. And let's just see what kind of performance we can get from one of these things. So this tab is an NVMe Direct VM. We're actually looking at an Azure Server host here with Task Manager running on the host. This is the VM with an application running in it that I'm going to launch. You can see perfmon here. And you can see that we've got 0 IOPS going right now, but I'm going to press enter to run this little script. which is going to start to hammer the disk. And this is going to quiesce here at about 3.7 million IOPS off of one disk. One server. There's a bunch of disks in here. So this is actually cloud leading right now. There's no other cloud server that delivers this IOPS this high off of local SSDs. And you can see evidence that it's mapped directly into the VM because this is the host task manager, no activity on the host. Here's inside the VM as processing all those IOs. It's burning a lot of cores to do that. So that's a look at NVMe. So going to Azure Compute now. Let's take a look at the compute architecture, the architecture again, but this time we're going to focus in on the compute stack. And here you can see the different layers in the compute stack. You can see the global Azure Resource Manager, resource providers that operate at the regional level. I've already talked about NRP, the network resource provider. We're focused on CRP, the compute resource provider here. But you can see all these other regional controllers, RNM, Regional Network Manager, Regional Directory Service, the USLB service, the SLB service for region. All of those are going to be coordinating with cluster level services for smaller blast radius, managing a small subset of the servers, and then talking to the nodes. And then when you deploy a virtual machine, this is the kind of flow of information across all these different components because they're all orchestrating to get that data down to the servers so that you get your virtual machine up with a disk attached to it and networking. So we're going to spend the next 10 minutes or so going through this. So that was just a joke. We're not going to do that. Unless you want to. No. All right. We'll skip that. But we've been doing a bunch of things to make virtual machines easier to manage. And one of the things we're excited to announce this week at Ignite is giving you serial console access to your virtual machines. So if you're not impressed, wait. OK, hold your applause, hold your applause. I'll show you this in action. OK, so if we go to back here and go to the browser, I'm going to refresh these, and we're going to come back and I'll show you what those are in a second. But what I want to show you here is I've got a Linux virtual machine here running in Azure. And you can see that it's got two network interfaces on it. One of them is the Ethernet network interface, which is connected to the Azure network. And I'm going to do something that's going to simulate a problem that will come usually because of some corruption, some bug. But shows you, oops, actually I'm glad I didn't do that because I wanted to ping this virtual machine first to show you. So I'm pinging that virtual machine. I mistyped that. And what this command does is takes out that Ethernet interface. So the second I do this, those pings stop. And at this point, your VM is completely inaccessible. Or is it? If we go back to the serial console, I'm SSH'd into my VM through the serial port on the virtual machine by leveraging an agent in the Azure host, the server. So if I do this, boom, I've just fixed the network. But let's take a look. That's not just for Linux, it's for Windows too. I'm going to crash Windows here using another one of my favorite tools. This is a tool called Not My Fault that I wrote for Windows internals. And you can crash the system in lots of cool ways. I'm going to crash it in a simple way. I've just pressed the crash button, and this thing is gone. So now we want to see what happened to this. If we go to the serial console for my Windows machine, you can see what happened. It crashed. myfault.sys, this information spit out at the crash through the serial port. And now we can see it. And also, because we're capturing screenshots of the VM into Azure Storage, we can show you that in the portal too, so you can see here what happened with that VM. So that's a look at serial console access. So another way that we're advancing the state of the art with containers, besides giving them first-class citizenship in the Azure network, is to take them serverless. And this is something we announced here. You might have seen Scott Guthrie talk about it or Corey talk about it. It's virtual kubelet. What this is effectively an agent that plugs into a Kubernetes cluster, and behind it is whatever it wants. It could be a cluster of another type of compute, but to Kubernetes it just presents itself as a node, another server. One that has effectively infinite capacity. And we created a virtual kubelet that connects with Azure Container Instances, which is our serverless container service. You can just launch a Docker container into ACI. You don't have to create a virtual machine ahead of time, and the container will just launch into a serverless infrastructure. And so a virtual kubelet on top of ACI effectively makes Kubernetes serverless. If you had a Kubernetes cluster with 0 nodes in it, except for a virtual kubelet backed by ACI, you could start deploying pods to it, and they would automatically scale out onto ACI. We're also taking Service Fabric serverless. How many people have heard of Service Fabric out of curiosity? So quite a few of you. This is our own microservices orchestrator. It supports higher level programming language. It supports stateful microservices. We've built a tremendous amount of not just Azure, but Microsoft on top of Service Fabric. And you can see a list of some of the services here, like those core Azure resource providers, the compute, network, and storage are all built on Service Fabric. Cortana, Cosmos DB is built on Service Fabric, Skype for Business, Service Bus, Event Hubs, Event Grid, Power BI, Azure DB, Intune, and the list goes on and on. All of these operating at massive scale for years on top of Service Fabric. And we made this available open source for Linux and Windows. We've made it as a service in Azure so you can launch a Service Fabric cluster, but we're taking it serverless we're announcing this week preview of Service Fabric Mesh. With Service Fabric Mesh, we manage Service Fabric clusters in the background. You launch Service Fabric apps to the mesh service. You don't specify virtual machines. You just specify them as containerized microservices, and then we launch them and manage the virtual machines underneath them and do all the wiring and load balancing and everything else that's necessary to keep them running in a highly available way. I'm going to show you a quick demo of Service Fabric Mesh now and show you just kind of the scale capabilities that you can get with this. Oh, actually, that's in a few minutes. That's a different demo. You're free to stand out here if you want. No, I'm just kidding. Yeah, it's going to be the next demo after this, sorry. So here I've got a Service Fabric Mesh application, and it consists of a web front end plus 3 microservices that are the same. They're Fireworks microservices, and we pass in, they each have a replica count of 1, and we pass in the, here's one of them, replica count of 1. You can see we pass in which color the firework should be as environment variables. So that's the red one. If we scroll down, we're going to see the green one, and you can see replica count of 1, and then finally a blue one. And what this is doing is this right here. That's what this app is doing, just firing a few every second, red, blue, green, kind of randomly. We want to get something a little more exciting than this. So what we're going to do is launch this version of it, where all we did was take that application, set the replica count to 500, and I'm going to launch it right now as an update to that existing one, which is running on Service Fabric Mesh. So in about somewhere around 30 seconds or so, we're going to start to see this thing scale out. Should be coming along. Oh, there we go. We're scaling out number of replicas. So it's a third service like this. We didn't have to go say how many virtual machines we want. We're only paying for those containers as they run. If we shut them down, we're not paying anything more for any compute, memory, or anything else. So this is the power of serverless right there. So the other thing we're doing with containers is taking to the edge, and microservices in general. So you've heard about intelligent cloud, intelligent edge, our vision for computing that spans both, and we want the computing to be consistent across both. So that service fabric application, we want to make it possible for you to take that and deploy it on Raspberry Pi class devices. Now, you probably wouldn't really want to do that, but the point is that we want to make it easy for you to take a microservices app that can run in the cloud and also run it on on-prem edge devices or devices out in the real world. Same set of tooling, orchestration of the launching of those applications and updating of those applications through a consistent cloud experience. So what I'm going to show you is deploying a highly available cluster to a group of edge devices. I've got, okay, you can come out now. I've got this setup up here. Now this is a very expensive piece of IoT machinery. This extremely expensive and very dangerous. It's got a spinning wheel on it that if I put my hand in it, I would get in trouble. Now this thing is, and you can see that it's got a sensor that is preventing me from hurting myself. Now if I go to the demo machine, I'll show you that I've got actually that app running up here in the cloud. And this should be showing me that telemetry coming from that thing. It's not. What we should be seeing here is data spewing out here from that device here in this cloud-based portal with these application and the machine learning algorithms all running up here in the cloud. But what I'm going to do is push that application down to the devices. So if I go to the IoT devices here, what I'm going to do is create this highly available cluster out of the collection of those 3 devices. And for some reason, I'm not seeing those devices. Seems like I've got a network problem, apparently, that's preventing this demo from working. And it is connected to the network. So I should be seeing the devices here, but I'm not for some reason. So this is oh, here we go, sorry. They're here. There they are. So what I'm going to do is select them all and then say create edge cluster. So I was looking in the wrong place. I'm going to call this Ignite Edge Cluster. This is going to create a highly available cluster. You can see there, it's provisioning. So it's deploying a cluster to those 3 IoT devices that are managing that, connected to that very expensive piece of machinery. And now I'm going to deploy a bunch of apps to them. So run on web app, run an Ignite, this edge. So I'm deploying the machine learning protection app, which is using vision recognition to determine if there's some object obstructing those in front of the device, and it's going to turn it off. So this will finish deploying down to those devices, hopefully in a second here. And the whole idea here is I want this thing to be highly available because this machine can't be offline, but it needs to be safe too. So I need to run that machine learning algorithm on that device, and I need to have it be able to tolerate failures of components like those Raspberry Pis. It's taking a while to deploy. So this might be lagging. I know what. Do a refresh here. And yeah, okay, they're running. Their status is running. So let's go back now. And what I'm going to show to demonstrate this high availability is I'm going to unplug this device and the network hub this device is connected to from the network. So I've just unplugged it right there. And not only that, but if I so once I've done that, if I come back over to the machine, I've got another view of the portal running on this system that is talking to those devices, and you can see that it stops collecting telemetry. Wait, I don't know what just happened. That's not what I meant to do. Oh, that's the wrong, oh, here we go. So well, you can see that the machine learning app is running on edge device number 3. And so what I'm going to do is go unplug edge device number 3. And at this point, we should see that this controller, this monitor, see that that device is offline. We're going to see an automatic failover that the highly available cluster is doing. We can have both Kubernetes and Service Fabric apps you can see on this thing. And there the machine learning API moved, and you can see that I'm still safe. So that is disconnected, highly available deployment from the cloud using microservices that are also consistent across the cloud and on-prem. So that's where we're taking that. Thanks. Now, the other thing one of the other things we're doing with compute is that we want to protect your data. If you came to my session earlier in Microsoft Mechanics, you saw me talk about something called confidential computing. The idea is that there's lots of threats for your data. And there's even potentially different kinds of threats when you put your data in the cloud. There's third parties that might request access to your data. There's hackers that might breach the infrastructure and get access to your data. And so we take steps, lots of steps in defense. We spend $1 billion in cybersecurity. But we also implement capabilities like encryption for our services at rest, encryption in transit. Applications can also encrypt their own data in transit. But what's been missing up to now is protecting the data while it's in use. And the cloud is not very useful unless you can process that data to get insights out of it, machine learning, analytics. And if you can't do that while fully protecting it, then you're missing one of these three. So with confidential computing, which is based off of this black box kind of technology called trusted execution environments, you can stick your data in a TEE, and then it's isolated from everything outside of it. There's two types of TEEs, software and hardware. An example of a hardware-based one is Intel SGX, where the processor itself creates these black boxes. They're encrypted portions of RAM, where the CPU is in a special mode. Nothing can get into that mode except for the code that is intended to run in that enclave. And what you can do then is you can get an attestation from the enclave. What code are you running? And it will produce a quote signed by the processor that says, this is the code I'm running. And then from the outside, you can verify that that truly was an Intel SGX processor by looking at the public key for that processor. And then verify that it's the code that you trust. And once it is, establish a secure channel with that code and hand it keys so that it can decrypt data into its enclave and then process it safely, protected by this black box. And the kinds of scenarios, so actually for confidential computing, we're just announced the availability of the DC series, which are SGX-enabled virtual machines. You can go launch them right now in Europe and US. And we're also announcing the release of an SDK to help you write confidential applications. One of the coolest scenarios that this opens up is something called multi-party machine learning. And what I'm going to show you is the power of multi-party machine learning here. Oh, you know what? Proof that that is a real demo. Okay, so connecting back to our demo VM, and now we're going to go into a virtual machine that is one of those DC series virtual machines. And those DC series virtual machine is right here. So I've got two hospitals. They're represented by different desktops, and they both have breast cancer training data that they don't want to share with one another. But they'd like to combine them to get deeper insights. And so the first thing they're going to do is encrypt their data to the enclave. So I've just encrypted it, and then they're going to upload it to the DC series VM. And we're going to do that with user B as well. Here's user B's desktop. We're going to go to drag this, encrypt it, upload it. We're signing as user B. And this data is encrypted so that only that machine learning enclave can see it. Now it's doing training run over it. We're going to switch back to hospital A because the goal here is to get back a trained machine learning model. So we're going to go to model and we're going to download it. Now we're going to go to evaluate the model. And we see that the local model, if we do an evaluation on the local model, we have an accuracy of about 84%. But the model we just downloaded from the cloud, from that combined data set machine learning, for that data from the other hospital, you can see it's a 97% accuracy. At neither point did either hospital expose its data to the other one or to anything else, including the cloud. Azure administrators don't have access to it. The hypervisor doesn't have access to it. The hospital, of course, doesn't have access to it. And so that's the promise of confidential computing. So let's talk about storage now. An Azure storage architecture is tiered architecture. So you have APIs on the front end. And those API sets continue to grow. So Blob was one of the first ones that we had. We have Azure Queues, also built on top of Azure Storage, Azure Files, and then we've got SMB as well. And there's load balancers that are on the front end, so load balancing traffic, sending those requests to front ends. There's a table tier or partition layer. This is where the data is partitioned, and the partition mapping to stream layer, or this extent layer down here at the bottom, this distributed file service across the servers. So a particular blob might be broken up into chunks that are on a bunch of different servers, and every one of those chunks is replicated 3 times for high availability. And then if you use a GRS storage account, where it allows you to replicate your data into another region, then that's copied to another stamp asynchronously in that other region. We've just announced recently Azure Data Lake Storage Gen 2, which is a massive scale-out data lake service. It's built on top of Azure Storage, but now it includes an HDFS front end, the Gen 2 API, and the Blob API. It supports hierarchical file systems. This is something that we added on top of Azure Storage. And the reason that we could scale out the way we did to support these data lake type scenarios, which are massive files, massive accounts of lots of big files, is by re-architecting storage. To take what used to be vertical monoliths of a storage stamp, where the front end was mapped to the partition table, which matched to the stream servers, all on the same set of servers, to separate them out into different software tiers that can scale independently. And you can see the kind of scale this gives us for a blob. The throughput limit on a blob up until this, the 60 megabytes per second. With this, it's 50 gigabytes per second. And so you can upload a file now that used to take 15 hours in just a few minutes. We've also expanded our SSD offerings. So we have standard hard disk as an offering. We've got premium SSD as an offering. And we've just introduced recently standard SSD, which has performance that's more like a hard disk, but it has much lower latency. So it's 500 IOPS, 60 megabytes per second, like the hard disk offering, but it's single-digit latency rather than multiple-digit latency that you'd get from a hard disk. And then we've also introduced something called Ultra SSD, which we just announced here at Ignite. This is our next generation disk storage, the purpose-built block storage service. It's called Direct Drive, codename Direct Drive, because the hosts that the disks are mounted to have information about which servers in the Direct Drive cluster have the relevant pieces of the files, of the VHDs. And so it can go talking directly to them to write and read data, rather than going through the load balancers in the front end and the partition table servers that even premium SSD traffic has to go through. So how many people saw Corey's Ultra SSD demo? Raise your hands. All right, so a lot of you haven't seen it, so I'll show it to you really quickly here. And so here I've got an Ultra SSD server. By the way, these support up to 64 terabyte drives. I'm going to launch this tool called Iometer, which hammers the disk as fast as it can. Now, this particular virtual machine is provisioned for 160,000 IOPS, which is the most you can get out of any single disk in any cloud. And to show you how consistent that performance is, here's Iometer's IOPS per second. You can see it's hovering right just around 160,000. And the latency is a millisecond or less. Also interestingly, that's what Corey showed, which is pretty impressive. But how about this? I've got a special server with a special disk on it that will show you that this technology is capable of going higher. So we're working on making even bigger, faster disks. And this is a preview of that I wanted to show you. I asked the team, beg them so that I could one-up Corey. So let's fire this one. That's 250,000 IOPS. And the latency is still about 1 millisecond. So we're going even further with our disks than we have than what I just showed you. Okay, so now I want to take you inside of our data platforms and talk a little bit about the database architectures that we've got. So when you take a look all the way out, many of our data services, including Azure SQL Database, Azure SQL Data Warehouse, and Cosmos DB, have this similar type of high-level architecture, where you go from regions. Each region consists of multiple data centers, like I also already talked about. There's the concept of stamps. So they have got deployment groups of a number of servers, typically on the order of thousands of servers. Those stamps have what are called fault domains. And a fault domain is a single point of failure, group of servers that have a common single point of failure. In our data centers, that would be a top-of-rack router or a power distribution unit. If one of those fails, you lose those servers. And so we need to make sure that those storage services understand fault domains, and so they can spread data out among them. I mentioned 3 copies of data. Well, actually, with a premium Azure database, database, you get 4 copies of data. So 4 copies spread out across different fault domains. So if you can lose 2 servers and still be able to write to your Azure database. Now, within a machine, you can see that there's a bunch of agents, there's containers that are running those databases instances. You can see there's resource governors. There's a transport layer that allows that database to connect to the outside world. There's admission control that throttles on the way in, traffic, so that the user gets the throughput that they provisioned, and then the database engine itself. And the database engine, of course, has a query processor, language runtimes, and so on. That's the overall architecture. Now, how many of you have used Azure SQL Database? See, raise your hands. So quite a few of you. How many of you have ever wanted to raise the RUs, the request units on your database, and then only to experience the fact that you've got downtime as the database gets resized? Anybody? Just one person? So this, I'm talking to you then. Everybody else can ignore this section. No. Well, I'll explain the kind of experience that the few people that raise their hands have, because up to now, what we've done is co-locate the database with the data that it manages on the same server. So there's multiple replicas, like I mentioned. In the case of Premium, there's 4. So there's 4 servers, but one of them is the write master out of those 4. And when it writes to its local disk. It also sends the data to the other replicas for them to write to their local disks. But you can't scale up the compute independent of the storage, because there's a one-to-one mapping with these replicas and the data on their local disks. So what we've done is re-architected Azure Database to break that connection between compute and storage. And this is actually a trend across data services in our cloud in general, is to separate compute and data, which will allow you to independently scale the compute and the data. In fact, you can shut down the compute and still preserve the data, something you couldn't do with this previous architecture. Here's a diagram of this new architecture. We call it Socrates, codename Socrates, but the official name that we're thinking of it is Azure SQL Database Flex Scale. And you can see that there's the compute tier at the top. You can see that there's 4 replicas, like I mentioned. One of them is the write master, and that's the one on the left. You can read and write to it. The other ones you can read from, so it scales in read as well. And you can scale out this tier, so you can have any number of read replicas to scale out the amount of data queries that you can do against the database. Now, the way that we get this separation is by storing the log on a premium storage SSD. So the log gets spit out to the SSD. That log is then read by from these storage stamps that then do the commits of or do the serialization of the transactions in the data store. So any failure at any point, you either have the logs or you have the data in storage. And now the data in storage can be read into any of those read replicas or the write replica for read operations and transaction processing for writes. So like I said, we could take that compute tier and shut it down, and that data is still sitting in storage. Or we could take that compute tier and scale it out. And that's exactly what I'm going to show you now with the demo of Azure FlexDB. It's the first time shown publicly the dynamic scaling out of a database. And what this also does is let us break the database size barrier. So the maximum size, anybody know the maximum size of an Azure SQL database today? Anybody? Anybody? You could ask Cortana and she'd probably tell you. 4 terabytes. So what I'm going to show you here, here's my Socrates database. And it's 50 terabytes. And we're going to 100. So this is where we are right now. We're working on scaling. So we're at 50. We wanted to give you a preview of what this is. And you can see this is a premium L1 database with 250 DTUs. So the DTUs are the amount of query processing that this database will support. In the past, like I mentioned, if you had an L1, to create an L2, to scale up to an L2, what had to happen was you had to shut down that L1, create the L2 on a bigger server, and then copy the data off of the L1 servers onto the L2 servers, an operation which could take tens of minutes or hours. And in a 50 terabyte database, that's going to be a while. But we want to be able to scale while this database is running and without having to copy the database. So what I'm going to do is go into this is, oh, not there. Getting lost in my demos. So that is over here. Here we go. So this is the, I'm going to send a SQL command into that database to scale it up to an L5. Execute that. Oops, I need to select the whole line. And this is going to take about 2 minutes. So we're going to come back and look at that in just a couple minutes. But we're going to see this thing dynamically scale out without the hours that it would have taken otherwise. So finally, I'm going to conclude by taking a look at Cosmos DB. Cosmos DB is a relatively new database. It's a NoSQL database. But I think it really represents the pinnacle of, or kind of the cutting edge of cloud-native databases. It's got a number of different characteristics which are unique to it in the public cloud. For one, it's a multimodal database. It supports a number of different APIs, from the Azure Tables API to a SQL JSON API to MongoDB. We announced Cassandra this week. And you're likely to see even more. Gremlin Graph API. But besides supporting multiple APIs, it also supports multiple consistency levels. So you can, on a standard database, you get strong consistency, but you sacrifice performance for that. So the NoSQL movement was saying, hey, we're going to be inconsistent, asynchronous, and that will let us scale better. So Cosmos DB lets you go fully to asynchronous, fully to synchronous, and has 3 levels in between, including the default, which is session consistency, which is typically what most applications need, which is anybody participating in this session with the database sees the reads and the writes in the same order. But now different applications with different sessions that aren't interacting with one another can be operating in parallel. And that allows your database to get much higher performance, even though it's technically inconsistent. It's also designed for massive scale. It's designed to work across regions, and it's the only database in the public cloud that supports SLAs across 5 dimensions. So latency, consistency, throughput, availability, and there's a 5th one. It's a homework assignment. But if you take a look at the Cosmos DB architecture, it splits databases into partitions. Those partitions are split into are replicated to multiple regions. And so you can replicate literally to every region in Azure a single database. And within a region that's got replication turned on, you can see that there's like a virtual replica. So we saw in the SQL database that there was 4 replicas. They were all writing to local or reading from local. In the case of Cosmos DB, there's a single write master, but there's also a proxy to another region that participates in quorum and is writing data off to other regions. And so that is the way that Cosmos DB works across regions. Now to show you just how incredibly scalable Cosmos DB is, I'm going to show you a demo that should drive the point home pretty well. Let me see how my FlexDB is going. And there we go, Premium L5 with 4,000 DTUs. So we've scaled out that database in just a couple minutes from 250 DTUs to 5,000 DTUs, something that would have, with a 50 terabyte database, would normally have taken a few hours in just a couple minutes. So that's Cosmos DB. Now I've got one last demo to show you, and that's this Cosmos DB demo. And here's the portal. So what I've got right here is an example of an app. It sells tickets. It's a ticket selling app. And we've got one region that is active and writing to the database right now. So we've got this app, this GUI is basically a load generator simulating lots of people buying tickets to some event. We only need one region. We're selling about 11,000 tickets per minute, and you can think of that as transactions per minute. And this database is a 100 terabyte database, shows the kind of scale, the size that Cosmos DB databases can get to. You can see the latency that it's reporting here across all of the regions that it's writing from, the average across all, and you can see it's 6 milliseconds to 9 milliseconds. Under the 10 millisecond 99th percentile SLA that Cosmos DB has for reads and writes will always be, as our promise, at the P99th percentile under 10 milliseconds. But let's say that we've got a surge in ticket sales. So I'm going to go into panic mode, which is scaling out the database writes to handle that increased load. So we're scaling out to another 2 regions. There's a total of 3 regions now. The reason it looks like 4 is that this is a wrap around so that you can see that this Asia is the same as this Asia. And you can see when we hover the mouse over it, the latency of writes in that region, 8 milliseconds, 5. So we've got writes coming from all over the world, effectively ticket sales from all over the world. You can see our latency average across all of those writes. We're driving now 500,000 transactions per minute as ticket sales, updating this database. How's that? Okay, I'm glad you found that kind of impressive. So I'm going to take it up a notch. We're going to go into extreme panic mode because it's been announced that Scott Guthrie is going to be at this event. And so now ticket sales are going crazy. And we're going to scale out now to 20 regions. And we're going to support, as you can see this scaling up here, 782,000 tickets per minute, 1 million tickets per minute, across 20 writes going from 20 regions, multi-master write capability, so the writes can happen close to where they're being created at below 10 milliseconds latency on a 100 terabyte database replicated to 20 regions around the world. And to show you that in how you configure that in the portal, that was my connection error from disconnecting from the network, so let's get back to this database. This is the actual Cosmos database. What? That's not it. I think this is it. Hopefully I have access. No, I don't think this is the one. I think it's in a different. If I go to replicate data locally, globally, we should see 20 regions. Oh, no, we don't. This is not it. I don't think it's this one either. So maybe I'm logged out now and oh, nope, that's not it either. But what you would do is select the regions that you want to replicate to. It's as simple as selecting them on this UX or obviously programmatically. And if I went to the overview on the database that I was just hitting, the number of transactions that database has processed, because we started messing with this demo yesterday, and so that database has been online since yesterday. We've been hammering it, running this test up and down, is 1.5 trillion transactions since yesterday, is what you would have seen, across 20 regions, 10 millisecond latency or lower, multi-master write capability. So really, that's all of that combined is why I think Cosmos DB really is at the cutting edge of where data services are in the cloud. So with that, I want to wrap it up. I hope that you found this interesting and hope it gave you a little look behind the covers of what our Azure Data Center hardware infrastructure and software infrastructure looks like, as well as showed you some of the cool innovations, many of which we've got coming out here, and then I'll give you a preview of some things that are going to be coming, directions we're going. So with that, I want to thank you very much. Have a great Ignite, and I'll see you tomorrow if you come to the Blockchain Talk.